All right, so here we are again for the second part of the lecture for today. This is part 2 of lecture 3 of ENGR 2302 Engineering Dynamics. So we have covered rectilinear motion quite thoroughly, or reasonably thoroughly, or we've pretended to, one of those. And now let's talk about curvilinear motion. So if rectilinear motion was motion in a straight line, then curvilinear motion, you won't be surprised to learn, is motion in a curve, or motion that is not constrained to along a single dimension. So let's look at curvilinear motion. Oh, that's not good. Curvilinear motion. Okay, so I would like to define the position vector of a particle. Basically, position vector R of a particle at time t is defined as the vector from the origin to the particle's position at that time. Defined as the vector from the origin to the particle's position at time t. Let me check something really quick. Okay, we're good. Okay, so again, position vector R of a particle at time t is defined as the vector from the origin to the particle's position at time t. So let me actually draw that out. So let's say we had an x, y, and a z axis. Maybe we have an x-axis, a y-axis, and a z-axis. And then let's say the object's path is just some arcing path. And it could be two-dimensional, it could be three-dimensional, whatever you're working with. And maybe we go from 2 points. At some point, we have maybe a P, and at another point, we have P prime. And then you have vectors R and R prime. So maybe P is the initial value and P prime is the final value. Actually, let me go ahead and erase that arrow here just to indicate the path of motion. So this would be R, and this would be R prime. And then the vector from one to the other, so these would be vectors, R and R prime. And then the vector from the ends of each vector would be delta R. Would be delta R. I want this to be, so in case you can't tell by my poor art skills, R, R prime, and delta R are all meant to be straight lines. This is delta R, the change in position vector. And then delta S is going to be the change in the actual length of the path this object will take. So the actual length of the path would be something like delta S. So delta R is just going to be, delta R, again, is just the change in position vector. Change in position vector. And delta S would be the actual path length. And if this was motion in a straight line, these would be the same if it's a curving path or a a series of straight lines or something like that, that would not be the same. Okay, so we're talking about the difference between displacement and distance traveled, essentially. Okay. So let us look at this here. All right, so let us compare instantaneous velocity to instantaneous speed. Instantaneous velocity to instantaneous speed. Well, instantaneous velocity is going to be, let me draw the same coordinate system. So two sets x, y, z, and instantaneous speed. All right, so this is going to be, again, let me mark these paths. Let me see, I used purple and red. So let me make my curve again. Two curves, these are just generic curves, can be anything really. And then R and R prime. So let me label this here. R and R prime. P and P prime. P and P prime. And let me provide the definition of instantaneous velocity. Well, instantaneous velocity is going to be a vector. So notice I'm giving it a vector sign. The other one will not. It will be the limit as delta t approaches 0 of delta r over delta t or dr vector dt. So it can also be thought of sort of, okay, think about this. As these two converge, as r, so this, the difference between p and p prime corresponds to a certain time t. As this time shrinks, this arrow is going to move, these two arrows are going to move closer and closer and closer together. Eventually they'll be right on top of each other. So when they're very close together, the delta r, which is from here to here, if you remember, is going to be essentially the slope of the line. Although it's going to be a vector because this is, I can't really talk about slope in 3 dimensions, so it's going to be the vector there. Or I could say, let me show a third vector on here. The vector, looks bad. This vector from P to P prime is going to be delta R over delta T. Delta R over delta T. This vector here. All right, so again, this is a instantaneous velocity. I want you to be keep in mind is this is a vector. In comparison, instantaneous speed is going to be a scalar. It's going to only have magnitude. Instantaneous velocity is a vector. Instantaneous speed is a scalar. And so I can simply say, if I have an R, this is going to be looking at just a moment in time, R. And then, if I were to look at, say, P and P naught, and then initial P a few seconds before, or a little bit of time before, again, the distance along here is S. the distance along here is s, the arc length, you might think of it as, through a circle. The distance along here is s. And so here, I'm going to use v again, but I'm not going to use a vector, is the limit as delta t approaches 0 of delta s over delta t, or ds dt. ds dt. And here the velocity, again, would have a vector like this. So this would look something kind of like this. This would be the magnitude here of v. Another way to think of this is the magnitude of this. So if you have the vector, you can find the magnitude of it by taking the combined, basically find the magnitude. Just like you would find the magnitude of any other vector, you can sort of think of it as finding the Pythagorean, although that's not really exactly proper, but it's basically taking the square root of the sum of the squares of the three rectangular components, if you happen to have it in rectangular format. All right. Moving on, now let's look at acceleration in graphical form. So acceleration for curvilinear particles. Well, for acceleration here, consider a velocity, a particle with velocity v vector at time t, and let's do v prime at time t prime. Or actually let's do t plus delta t. That looks way too many t's like, so I'm going to make sure to get my t at curl. Plus delta t here. Okay? Fundamentally, a acceleration vector is going to be the limit of delta t, as delta t approaches 0, of delta v over delta t is equal to dv dt. And this is instantaneous acceleration, which is a vector. And we can find the magnitude of this if we wish, but we usually don't give it a special name like we do the magnitude of velocity, which is speed. All right, so if I want to combine this together into one plot, it would look something like this. If I had let me draw an object again on a certain path, x, y, and z. If I have an object on a certain path, so I would have, again, maybe p and p prime. And then let's say at this point it had velocity v and v prime there, and then v prime here, v prime here. At this location, the acceleration is going to be whatever inducing the change in the is going to be whatever is inducing the change in velocity at point P. So in other words, it might be something kind of like this. If it were circular motion, it would be exactly perpendicular, but I don't want to say it's exactly perpendicular, but in the case of circular motion, it is. But as a rule of thumb, in general, acceleration vector is not tangent to the path and velocity vector. A is not tangent is not tangent to path or v. All right, so let us look next at the components. Let us look at this in terms of components. I want to look at the curvilinear motion in terms of components. Okay, so rectangular components of velocity and acceleration. We'll be working a lot with rectangular components. Of velocity and acceleration. Okay, so let's look here. And let us create an x, y, and a z axis. X, Y, and Z. And then along here, I will have unit vectors I, J, and K. Unit vectors I, J, hopefully you can read this. I know I'm realizing now that purple is a poor choice for this particular label. But it's just unit vectors I, J, and K, which you've all seen before. And then if I have a position, well, let's think about this. Let us first look at velocity. So I'm going to have a particle at some position P, and I know that it's going to have vector R. To that point. So I have vector R, and vector R is going to be xi plus yj plus zk. The x, y, and z components of each of these. The x, y, z components of this position. And you should be very familiar with this from statics. If you remember back last semester or 2 semesters ago, whenever you took it, you may remember back to statics where you found the components of moments and all of that kind of stuff. Remember that fun stuff? Wasn't that so much fun? And now it comes back. Joy. You thought you were done with it. Nope. All right, so then let's consider here. Let's say that I have, and let me actually maybe label these. So if I take this down, this would be, this component, if I drew it like a vector, would be yj. This one here would be z, yj. This would be, this vector here would be zk, and this one here would be xi. Then I could write the velocity. I could write out the velocity vector. And it would be something similar. I would have a velocity vector here. And it would have components. Let me show colors. Maybe in yellow. No, that's a terrible choice. You probably can't. Can you see that yellow in the back? If I do that, can you see this? Can you read that in the back? Or is that too light? You can see it? Okay. Maybe I'll use a different color. Then let me use green. So this would have components. Well, this would be Vx. And then, let's say, well, it looks like it's almost going like that, so. VZ in this direction, and Vy. Drawing this many 3D vectors is always difficult. So the velocity vector then, the important thing is more of the math. The velocity vector, so again, this is the position, let me label this as the position vector. The velocity vector will be, well, velocity vector V is equal to dx dt times unit vector I plus dy dt times unit vector j plus dz dt times unit vector k. Or I can also make this simply vxi plus vyj plus vz k. And in similar vein, the acceleration vector, which I could also draw it out if I wanted to, but I think you get the idea of just having a vector and drawing it out into components. I could also go then and say that the acceleration vector, if I had a little more time, I would actually draw out the acceleration vector, but I think it's fairly straightforward. The acceleration vector, well, acceleration vector A is going to be the second derivative of x with respect to time times the unit vector I plus the second derivative of y with respect to time times j plus the second derivative of z with respect to time, and that is times k. And I also want to perhaps label this a little bit differently. I want to use my dot notation as well. This could also be labeled x dot I plus y dot I, or y dot j, plus z dot k. If you ever see me use the dot and you aren't familiar with what that means, dot means one dot means the derivative with respect to time once. 2 dots means the derivative with respect to time twice. So I could also say here on the acceleration, this is equal to x double dot I plus y double dot j plus z double dot k. Or I could simply say this is axi plus ayj plus az times k. All right? All right, so let's move on then. Some more discussion of this. Okay, so jot that down, take a look at it, but we're really getting into the hairy math here. But let's look at some cases where this is particularly useful. Don't worry, I promise to look through at least an example or two. Okay, so when is this useful? Well, let's think about this. When are rectangular components useful? Well, rectangular components are particularly useful when the components are independent. Can anyone think of a case where that might be? When the x, y, z motion of a particle when those three motions are independent. Can anyone think of an example of that? When the motion in the x does not affect the motion in the y, does not affect the motion in the z. Anyone think of an example of that? It's a fairly simple example.
Water?
Sometimes water, but I'm thinking of something even simpler. So you usually study it in basic physics. Well, you always study it in basic physics, if you study. But I assume if you couldn't pass high school physics, you're what did I just do? You're probably not here. I think I somehow zoomed out. Okay, there we go. Fixed. Okay, so an example is projectile motion. Consider the motion of a projectile. Consider the motion of a projectile. So, if you have an object that is in projectile motion, well, let's think about this. An object in projectile motion. Now, this is assuming that we're ignoring air resistance, as we often do in basic projectile motion problems. If you're allowed to ignore air resistance, then the x and y motion become completely independent. If you do have to consider air resistance, though, then the motion is not independent and the math becomes a lot more complicated. But if we are ignoring air resistance, then the motion becomes independent. So, say we have a particle at some position here. Well, this is going to have an x and a y coordinate at any given time. So this will have an x and a y coordinate at any given time. And it would be launched with a certain initial velocity. And so you'd have something like v naught, the v naught vector, and this would have a v naught x, and then a v naught y. Would have an x and a y component. So let us see what happens when I say, or see what I mean when I say the motions are independent. Let's look at this mathematically. Well, let's look at the x direction. The motion in the x direction is going to be the second derivative with respect to time of x double dot, and this is just going to be equal to 0. We have, if you remember back to elementary projectile motion, the acceleration in the x direction is 0. And then ay is going to be y double dot, and that's simply going to be equal to negative g. And then az, there is no motion in the z because I have actually conveniently defined my xy plane as along the path of the motion. So this is simply going to be z double dot, which is also equal to 0. And then I have initial conditions. With initial conditions, or boundary conditions, with initial conditions, x naught equals y naught equals z naught equals 0, and also vx naught, I would have some known value for that, vy naught, and then and also vz naught is equal to 0. So these two are not equal to 0, but they would have some known value, and this one is equal to 0. And then if you integrate twice, you can find further relationships. So I'm going to integrate these twice and get the equations of motion here for simple projectile motion. So integrating twice yields integrating twice will yield. So Vx is going to be equal to Vx naught Vy is going to be equal to Vy naught minus Gt, and Vz is going to be equal to 0. And so basically this is integrating and then putting in boundary conditions. X at a certain time t is going to be Vx naught times t, y is going to be equal to vy naught times y. Let's see, actually times t, I should say, sorry. Vy naught times t minus 1/2 gt squared. Minus 1/2 gt squared, and then z is simply equal to 0. So in other words, the conclusions of this are conclusions. 1, motion in horizontal direction is uniform. Direction uniform or constant. 2, motion in vertical direction is uniform acceleration. Is uniform acceleration. And 3, motion in z non-existent. No motion in z. And then lesson here. Motion in the motion of the particle, a projectile, can be replaced with 2 independent rectilinear motions. Can be replaced with 2 independent rectilinear motions. So 2 independent rectilinear motions. So this is where rectangular coordinates are very useful. If you have a system that you can break it down into 2 independent motions, x and y motion, or maybe even 3 motions, x, y, and z motions, in that case, it's something very useful. Okay. So questions on that? I think I'll run through a quick example of a maybe a projectile motion problem to illustrate this, and then we'll move on to some other cases further along. Okay. Here. Actually, let me check the time. Okay. Okay, so let us say we have a problem like this here. So let me do an example problem. So example, so let us say we have a particle that is launched, or a ball that is launched. We have the ground that does this cut that slopes downward here. And this thing is launched. This is basically just a simple physics problem, although we'll be analyzing it from the point of view of derivatives rather than simple equations. We're really doing it the hard way, because just using the equations of projectile motion are too easy. So we're going to take derivatives. So we have an object that's going to go in a path like this, something like this. It is launched from the top of a 150 meter high cliff. So this is 150 meters high. And the initial velocity is 180 meters per second at 30 degrees. 180 meters per second. It's going quite fast. At an angle of 30 degrees. 30 degrees. We're going to ignore air resistance, so all of this is given basically. And I want to find x and the max height. So this is going to be x. All of this is given. Given. find x and the max height. Max height above ground. Above ground. All right, so let us look at solution. So I'm going to define this as y0. Or sorry, I'm going to define this as my origin, my 0 coordinate. So I'm going to relist my givens, but in a tabular format. Basically, V naught is 180 meters per second. Y naught, the initial vertical position, is 150 meters. The A in the Y direction, well, actually, this is an assumption. I wasn't given this, but I'm going to assume this is on Earth. It might not be. We could have a cannon on the moon, but anyway, it's for our purposes here, it's going to be on the Earth. That's one of my favorite things to do in certain problems, like fluid mechanics problems, maybe in dynamics problems too. I just love taking a problem and just adding one little sentence like, "This system is on the moon." Just makes things so much fun. But anyway, negative 9.81 meters per second squared. And then the acceleration in the x direction is equal to 0. So all of this is given. All right, so I know then that I can analyze the horizontal and vertical motion independently. And I should also say it was also given that air resistance is 0. Air resistance is, approximately 0. We can just assume that's 0. So again, because this is projectile motion, I'm going to treat it as a simple rectilinear, a set of 2 rectilinear motion problems, and I can use the component method and analyze the x and y motions independently. So I'm going to have to I'm going to break this down into x and y motions. That's not right. It's not slide 7. It's slide 17. But oh well. Let me fix that. That's slide 17, not slide 7. And I know we go through this fairly quickly, but we have a lot to get through in this class. Okay, so that's also one of the reasons I'm posting these online. So hopefully you can go back if you missed something and go back and check it over again, etc. So let's look at the vertical and independent. I'm going to look at the vertical and horizontal motions independently. Again, I can do this because it is a projectile motion problem. We will not always be able to do this, but in this particular case of problem, we can do this. So vertical motion, this is going to be under uniform acceleration, uniformly accelerated. Vertical motion, uniformly accelerated. And I know that, let's first find the Vy naught, the vertical motion in the y direction. And that's simply going to be 180 meters per second times the sine of 30, times the sine of 30 degrees, which comes to plus 90 meters per second. And then Vy is going to be equal to Vy naught plus At, which then becomes Vy equals 90 minus 9.81 t, and then y is equal to Vy, basically the integral of this, Vy naught times t plus 1/2 at squared, and y then is equal to 90t minus 4.90 t squared. Or I could also say Vy squared is equal to Vy naught squared. So basically I'm just working through the equations of uniform motion that we saw earlier, that we saw on Thursday. 2ay or simply Vy squared is equal to 8100 minus 19.62 y. All right, 19.62 y. So I have these equations, and then I wish to look at horizontal motion. I haven't yet solved for the actual things requested, but I'll get there. And I'm going to call this one here equation 1, this one equation 2, equation 3, and we'll see some others later. Horizontal motion. This is zero acceleration, or just uniform motion. So I'm going to choose the positive x-axis as moving to the right from the launch point. And then I'm simply going to say Vx naught is equal to 180 meters per second times the cosine of 30 degrees, or is equal to plus 155.9 meters per second, and then x equals Vx naught times t. There is no acceleration, so we can just say x at a certain time t is equal to 155.9 times t. Now I wish to find the horizontal distance. So let's continue to work through this. Horizontal distance. So to find horizontal distance, I know we're going through this fairly quickly. To find horizontal distance, projectile strikes ground, impact at y equals negative 150 meters. So I can substitute into set equal to equation 1. And I will get negative 150. Basically, I'm trying to get the time. Negative 150 equals 90t minus 4.90t squared. And then if we solve for t, solve the quadratic, you will get that t is equal to 19.91 seconds. And then if I want to label this as equation 4 here. This is going to be my equation 4. Actually, let me do that in green. This is going to be equation 4. And if I sub this time value into equation 4, sub time value into equation 4, I don't know why I'm using Roman numerals for this, probably not as convenient as it could be, and I will get that x is equal to 155.9 times 19.91 seconds. That's a long time for a projectile to be in the air. Is equal to 3,100 meters. And then maximum elevation is when Vy is equal to 0. So I can simply look at the Vy equation, which was equation, this one here, equation 1. So I can say 0 equals 8,100. Actually, sorry, not equation, not that one. I want to look at this one here. Sorry about that. Equation 3. Vy squared equals 8,100 minus 19.62y. 8,100 minus 19.62y. And I will find that y equals 413 meters. So then these will be my final answers. I'll put a box around them. This will be my, my final height, and this will be my total downrange distance. So this thing is going to travel over 3 kilometers before it finally hits ground. Oh, actually, no. I should be a little bit more careful. I said it launched from y equals 0, right? No, let's see. Yeah, so I say no, it didn't launch from y equals 0, but let's think about this. I said it launched from, y equals 0. So I'm saying the initial y was 150 meters. Actually, you know what? That doesn't maybe make sense. I don't like that. I think I like this one better, I think. Although maybe I need to think about that, because let's think about that here. The question is whether I add another 150 meters to say the max elevation above ground. I don't think we need to, because we already said that the initial y was 150 meters. Maybe I'm wrong, then let me think about that. Because we said let's trace this back. Okay, this is the change in y. Sorry, the y here is going to be the change in y. We didn't have an initial y. We actually basically did say the initial y was 0. So we can't do that. We actually have to go and say, this is going to be the change in y from the initial location. So the actual final max height above ground is going to be 413 plus 150, or 163 meters. Or sorry, 563 meters. 563 meters. And that will be our final answer. Yes, I know that was, sorry for the confusion there. Again, because if you look back here, this doesn't have anything about the initial height in it. There is no like y naught plus y0 or something like that. There's no, we're assuming, the way this equation is looking at essentially the change in y from the initial. And so if I had a plus y naught, then I wouldn't need to do this. But because I don't, I do need to add a final 150 meters to look at the actual overall final height above the surface of the ground. But if we look back at this, if we reflect on this, what we can say is the essential idea is that we're going to, I know I went through this fairly quickly, but you can hopefully come back and look at it. I know you may have missed something here or there. That's the only unfortunate, that's the only drawback of this format, I think. But that's also why I do post the slides and the videos online. So if I reflect on this, the whole process again is I'm going to come back and break this apart into x and y components. I'm going to break my entire system into x and y components and analyze them independently. Okay? I'm going to break my entire system into x and y components and analyze them independently. And I can only do that in very particular types of problems. I can only do that in problems that can be considered with their x and y motions independently. All right, so let's move on. Okay, so let us look at something such as a motion relative to a frame in translation. Motion relative to a frame in translation. What if I had motion relative to a frame in translation? So, often we need to look at motion relative to a moving reference frame. Often we consider motion relative to a moving reference frame. In fact, we usually do that even if we're not aware of it. The Earth is constantly moving, although we usually say that the Earth is a fixed reference frame. For most of our analyses, we will simply say, oh, the Earth is stationary. Relative to a moving reference frame. Example, but some more practical examples might be something like a plane's motion to the wind, to the air around it, to the wind, moving air. So a plane must move, but the air it's flying through is also moving. So you need to consider the motion of one relative to another. If you want to analyze the amount of lift that a plane's wing is generating, you can't look at the motion of it relative to the ground. You have to look at the motion of it relative to the air. So let's say you had a really slow moving plane, relatively slow moving plane. There aren't many planes that go this slow, maybe like a very light plane like a Cessna or something like that. And so this is where you'll see that I do not know how to draw airplanes. So let's say you had a plane, had some landing gear here or something like this. It's almost like a drone or something. So that would actually work. That would be a very relatively slow flying plane. And so let's say this plane is going very slow. Relative to the ground is maybe going 80 miles per hour. Relative to ground. But then let's say the wind is also going 80 miles per hour, but in the opposite direction. So this would not be a good idea to fly this plane into this wind, but let's say it got caught in a storm or something like that, and there is 80 mile per hour wind, so it's like flying into a hurricane or something. I don't know why you chose to fly your delicate drone, super slow plane into a hurricane, but today's your unlucky day, so you did. 80 miles per hour wind relative to ground. Let's make this like negative 80 miles per hour relative to ground. And we'll consider a more vector case after this. And then I'll label this as the plane. Well, here, what's the problem with that? Anyone know what the problem with that is? There's nothing wrong with how I drew this, except my poor art skills. But there's a lot of things wrong with it there. But in terms of the operation of the plane, how does that work? Oh, wait.
It wouldn't have to be going the other way, I think.
Derp. Yeah, never mind. And it helps if I draw the things in the right direction. What if this thing, so that would actually give it lots of lift. Let's go the other way. Sorry, I don't want a headwind. I want an 80 miles per hour tailwind. Right? So what happens there? The plane falls out of the sky. Why? Exactly, it's generating no lift. Lift comes from the relative motion of the air with respect to the wings. Lift produced by relative motion by air flowing over the wings. So a zero relative motion equals zero lift. And in case you didn't realize, aircraft are heavier than air. That's why it's called heavier than air flight. If this thing doesn't have lift, it is going to fall like the big pile of plastic and metal that it is. It's just going to fall right out of the sky. Now, hopefully, the pilot is smart enough and is a skilled pilot, and then the plane is built well enough that what you would do in this case is you would turn the plane as you're falling. So hopefully, you're not at that kind of. You need some lift over your wings, so you turn again into the wind or something like that to give yourself additional lift. This is also why, if depending on wind, it can be difficult or easier to take off from an airfield. Again, to get lift, you need to have motion relative to the wing. So if you have a tailwind behind you, a tailwind means coming from your tail. If you have a tailwind and you're trying to take off, it becomes much more difficult to take off. If you have a headwind, a wind that is coming towards you, that's coming from the front of your plane, you will have an easier time taking off. Anyone here ever, by any chance, ever worked on an aircraft carrier? Okay, occasionally I'll ask that and somebody will be able to answer these questions, but I don't know enough about the operation of aircraft carriers to say this for sure. But if there was a modest headwind, they might actually do this. I don't know enough about aircraft carrier operations to say whether they actually do this, but theoretically, they wouldn't want to do this in a gale. They wouldn't want to do this in a hurricane. But if there was a 20-mile-per-hour wind, and if they could spare the time and things like that, it might actually be beneficial for them to point the ship into the wind for the sake of giving themselves a little extra boost and a little extra lift. Would make it a little bit easier to safely take off from the aircraft carrier. But anyway, but maybe I'm wrong there. I really don't know much about how to operate an aircraft carrier. I'm just speculating from the point of view of physics.
Cessnas to the ground at the airport. So the wind can't, because you only need a 50-mile-an-hour wind to take off.
Really? You only need a 50 mile per hour,
55 knots, I guess.
55 mile per hour velocity, right? Or wind.
Well,
Okay.
winds.
Well, wind will do it. Same thing. Yeah. So, a 55. I'm told that a 55 for a Cessna, you only need 55 miles per hour to take off. So that means when they park them at the airfield, they have to chain them down because otherwise, a wind. It's not that difficult, even outside of a hurricane, to get. Well, it's fairly rare, but you don't need a hurricane to get a 55 mile per hour wind. And you don't even need sustained winds. A gust would be enough. And so you could, if you didn't, so a plane like that, a very light plane like that, you need to chain it down to the ground or weigh it down with sandbags or something, because otherwise just the force of the wind can lift it and send it tumbling or whatever, which would tend to damage a rather delicate airframe. All right, so how do we analyze these? Well, generally, we designate one frame of reference as fixed and then look at motion relative to that. So solution, basically how we analyze, to analyze, designate one frame of motion as fixed and then all frames not physically attached to this not rigidly attached to this, are moving frames of reference. So we'll have fixed and moving frames of reference. Moving frames of reference. So we might look at the, consider the air to be a fixed frame of reference, or we might consider the plane, etc. In most of our problems, we are simply saying the Earth is a fixed frame of reference. We are ignoring the motion of the Earth, even though we do know, again, that it does actually move, but usually that's simply not relevant to our problems. Okay. So if I were going to draw this out, it would look something like this here. So we might have X, Y, and Z, and O, and then our reference frame, or where our origin is actually moving. So our origin may actually move along with the new coordinate system, X prime, Y prime, and Z prime, but I still consider it as fixed. Then Z prime, and I might have an RA and an RB. I'm going to have a particle. Let's see, here and here, something like this. This might be point A, and this B. And I would have RB. And let me use a different color, that's a little confusing. RB and RA. Here. And then, and this here would be RB with respect to A. All right? So, further comments. position vectors of particles, position vectors of A and B, particles A and B, and B with respect to fixed frame of reference. Actually, I'm saying this is the fixed frame of reference, sorry. Fixed frame of reference O, X, Y, Z, or RA and RB, or RA and RB, RA and RB. And then the vector between is relative motion RBA. Okay? And then if you differentiate, take derivatives, well, I'll get that VB is equal to VA plus VBA, which doesn't surprise us. VBA is velocity of B with respect to A. And then if I took the other derivative, the second derivative, I would get A, B equals AA plus ABA where ABA is the acceleration of B with respect to A. With respect to A. And so if you want to find the overall motion of B, you can combine the motion of A and the relative motion of B with respect to B to get the, the absolute motion of B can be obtained by combining motion of A with relative motion of B with respect to moving reference frame attached to A. So I know that can be a bit confusing, but I think we'll see it more in later problems that will hopefully make a little sense. But again, it's all about relative motion, etc., etc. Motion of one to relative to another. It's all about we are going to designate a certain frame as fixed and then analyze motion relative to that fixed reference frame. So the final component, item I want to get at today is tangential and normal components of motion. Tangential and normal components of motion. All right, so motion tangential versus radial or normal. And normal components. We have another way of dividing motion. Previously, we looked at breaking motion down into x and y components, but we can also break it down into normal and radial components. So, tangential, of course, is going to be tangent to the curve. And normal, of course, will be normal to the curve. Normal or orthogonal to the curve. To curve. So if I have a path xy, if I have an xy plane, and here, so say I have just a random path, or a arbitrary path, xy. And then this object travels in an arbitrary path. I can say that this thing has two components, And I'm going to use E here. Let's say it has components ET for E tangential, or tangential, and EN for normal, EN. Rho, another thing I need to define, is the instantaneous radius of curvature. Instantaneous radius of curvature. And then V is equal to VET. So the velocity is simply going to be equal to the magnitude of the velocity times the normal component. And the acceleration vector is going to be dv dt of ET plus velocity squared over rho En. So the acceleration is a combination of the rate of, look at this closely. Acceleration is made up of both the rate of change of the velocity of the tangential component. So it is the rate of change of velocity, but it's made of the rate of change along the normal, or sorry, no, along the tangential with respect to time, plus velocity squared over rho, basically the centripetal acceleration. This can be thought of as the tangential and the centripetal acceleration. The vector is the sum of the two. Sum of the two. So a few notes here. Notes. The tangential direction ET is tangent to the path of the particle, to the particle's path. And the normal direction, EM, is perpendicular. The normal, EN, is perpendicular to ET. That should look more like an ET here. And points toward the inside of the curve. Points to the inside of the curve. And it can have, the acceleration has components in both directions. Acceleration can have components in both directions. Can have components in both directions. In both directions. Here. All right, so I think we're about out of time for today, so I think I'm going to let you go now. But I do have a little bit more material that I want to cover on centripetal versus tangential components, and I think I'll take care of that at a later time. So, all right, that'll do it, and as always, thank you.